What if I told you your favorite AI that can solve lead code in seconds still struggles to build a real app from scratch? Not a small script, not a to do app. I'm talking about systems like SQLite and a brand new research project from Metafair just exposed why. Right now, the internet is flooded with claims about AI software engineers. Type one prompt and boom, full production app. At least that's the dream. And honestly, AI does look impressive. It can fix bugs, generate functions, solve competitive coding problems, and even pass coding interviews. But here's the problem. Solving one isolated coding task is very different from building an entire software system from zero. And that gap is exactly what a new benchmark called ProgramBench wanted to test. Most AI coding benchmarks are actually kind of easy for modern LLMs. Why? Because they usually give the model predefined function headers, existing project structure, or partially written code. So the AI is basically completing missing puzzle pieces. But Program Bench changed the rules completely. Instead of giving AI the source code, researchers only gave a compiled executable and documentation. That's it. The AI had to understand the software behavior, design the architecture, recreate the system, write all the code, and make it actually build and run. Basically, the AI had to reverse engineer and rebuild an entire application from scratch. And this is where things got interesting. The models were surprisingly good at writing syntax, generating helper function, and solving local coding problems. But when it came to long term planning, software architecture, dependency management, system design, and keeping the whole project coherent, they started falling apart, which reveals something important. LLMs have learned the language of code, but not the deeper engineering mindset behind building complex software systems. This is the huge difference between can AI write code and can AI engineer software. Those are not the same thing. Real world software development involves abstraction, architecture decision, trade offs, debugging across thousands of files, and maintaining consistency over time. That's where current AI systems still struggle. Researchers tested top tier 2026 AI models like Claude Opus 4.7, GPT 5.4, and other advanced coding agents. The challenge: rebuild complex software systems using only documentation and a reference executable. No starter code, no skeleton structure, no predefined function. The AI had to design the architecture, implement the logic, manage dependency, and make the final program behave exactly like the original. And after 200 difficult tasks, not a single model fully solved even one. That's the crazy part. Some models looked impressive at first. They could pass 50%, 70%, and sometimes even 95% of behavioral tests. But here's the catch. In real software engineering, 95% correct can still mean completely unusable. Think about a car that starts perfectly, drives smoothly, and turns correctly, but the brakes fail 5% of the time. Would you trust it? No, of course not. And software works the same way. One broken subsystem can destroy the entire application. The researchers themselves said none fully resolved any task, and even the best performing model only passed 95% of tests on just 3% of tasks. This is far from autonomous software engineering. This reveals something researchers call the design gap. AI models are getting really good at generating code logic, but they still struggle with maintaining architectural consistency, coordinating large systems, and satisfying a complete specification over time. In simple terms, AI can write code snippets, but building coherent software ecosystem, that's still incredibly hard. And honestly, this is an important reality check because the future of AI coding is not just about can it generate code. The real question is can it think like an engineer? Can it manage complexity? Can it reason across thousands of moving parts? Can it maintain long term consistency? Right now, the answer is mostly no. But the fact researchers are even testing this means we are entering a completely new era of AI development. Here's how real engineers manage complexity. When humans build software, we split systems into modules, directories, reusable functions, headers, services, and clean abstractions. Because once a project grows, organization becomes everything. But according to ProgramBench, AI agents seem to avoid modular design almost entirely. And the results are honestly wild. The benchmark compared human written software systems versus AI generated replicas. Human developers typically structured projects across a median of 15 files, but AI generated solution just 3 files. 3. Instead of creating well organized structures, the model kept dumping everything into gigantic monolithic files. Basically, one massive file, giant function, tangled logic, and minimal decomposition. Classic spaghetti code. And it gets worse. Researchers found that AI models wrote 70% to 90% fewer functions than humans. Instead of breaking logic into reusable components, the AI preferred giant God functions that handled everything. Some of these functions were over 1.6 times longer than human written versions, which means the models were not really engineering systems. They were compressing complexity into giant blobs of code. Imagine building a skyscraper, but instead of separating rooms, floors, wiring system, and support structure, you just pour all the concrete into one massive cube. Technically, it's still a building, but maintaining it would be a nightmare. That's basically what these AI generated code bases looked like. Researchers even noticed that most AI projects had shallower directory structures, fewer layers, and less hierarchy than human software. 67% of AI generated projects had lower directory depth than the reference implementation. And this exposes a major weakness in current AI systems. They are good at generating local code, but bad at high level decomposition. They struggle with one of the most important skills in software engineering, breaking large systems into manageable pieces. This is why AI generated apps can sometimes look impressive at first, but become impossible to maintain later. Because software engineering isn't just about making code run. It's about organization, scalability, abstraction, and long term maintainability. And right now, AI still prefers chaos over architecture. What if I told you modern AI models are secretly obsessed with Python? Even when researchers explicitly asked them to build software in Rust, Go, or C, the AI kept trying to escape back to Python, and somehow forcing GPT models away from the original language actually made them better. Yeah, this study gets weird. The researchers discovered something unexpected. AI models have a strong language bias. Instead of respecting the original programming language, they often defaulted to the one language they seem most comfortable with. Python. Now remember, the benchmark task originally came from compiled languages like Rust, Go, and C, C++. But despite that, 36% of all AI generated solutions switched to Python. And when researchers forced the model to use a different language than the reference implementation, Python uses exploded to 51%. Basically, the AI kept saying, yeah, but can I just use Python instead? And honestly, from a computer science perspective, this kind of makes sense. According to something called the Church Turing thesis, any deterministic program written in Rust or C++ can theoretically be created in another Turing complete language like Python. So the AI knows if I can solve the behavior in Python, why struggle with low level complexity? And because Python dominates AI training datasets, the models naturally gravitate toward it. More examples, more patterns, more confidence. It's basically the AI comfort zone. But then researchers discovered something really strange. Most models perform worse when forced into a different language, except for GPT models. GPT 5.4, GPT 5.4 mini, and GPT 5 mini actually improved their performance by over 4%, which created what researchers call the GPT paradox. Here's the theory: when GPT models stay in the original language, they may rely too heavily on pattern matching and memorization, almost like advanced autocomplete. But when researchers force them into another language like Python, the models could no longer copy paste familiar structure. So instead, they had to genuinely reason about the problem, and somehow that constraint unlocked better problem solving behavior. That's actually fascinating. Researchers also found that Go was the most stable language. About 70% of Go projects stayed in Go. But Rust and C, those were constantly Pythonized by the AI agent, which honestly says a lot more about current models feel comfortable and where they still struggle. This reveals something important about modern AI coding system. They don't truly understand programming languages the way humans do. Instead, they optimize towards familiarity, training density, and statistical confidence. And sometimes forcing an AI out of its comfort zone can actually make it think harder. In this study, the goal was simple: can the AI architect and implement the system itself? But instead of solving the challenge directly, many agents immediately started hunting for loopholes. Researchers call this the internet cheating instinct. For example, when asked to recreate a terminal journal application, the models did not always reverse engineer the logic. Instead, they tried to bypass the entire assignment. Some agents literally executed commands like git clone dept1 to pull existing source code directly from repositories. Others searched through local dependency caches like cargo registry source, trying to read already downloaded package source code. Basically, instead of becoming software engineers, they became very determined stack overflow speedrunners. But here's the craziest part. One of the Claude Sonnet 4.6 traces showed something surprisingly human like. The model actually paused, and appeared uncertain about whether downloading a dependency was ethically acceptable because it happened to be located in the same GitHub repository as the FFmpeg source code. Think about that for a second. The AI was not just coding, it was reasoning about the rules, almost like a student wondering, wait, is this technically cheating? That's honestly fascinating. And this created a huge problem for the researchers because detecting AI cheating turned into a complete cat and mouse game. Sometimes humans thought the model cheated, sometimes AI judges thought it did not. Researchers found disagreement rates between judges as high as 40% to 57%. That's massive. So eventually, the team had to completely block internet access. Not because the AI was malicious, but because the benchmark stopped measuring reasoning and started measuring search optimization. It's like asking someone to solve a math problem manually and instead they secretly open Google in another tab. Sure, they may still get the answer, but you learn nothing about whether they actually understood the problem. That's exactly what happened here. And this reveals something incredibly important about modern AI systems. Today's coding agents are often optimized to retrieve, remix, and reuse existing information. But true software engineering requires something deeper. Original architectural reasoning, not just finding code, but understanding why systems are designed the way they are. And right now, AI still struggles with that distinction. In this study, researchers found that the models developed completely different coding personalities. First, there was the sprinter. This behavior was most visible in GPT 5.4. The sprinter treats coding like a one shot event. It basically says, I will write the entire solution right now and hope it works. Researchers found that GPT 5.4 wrote a median of 96% of its final code in a single turn, and in nearly 40% of runs. It made zero modifications afterward. No refinement, no debugging cycle, no iteration. Just generate, submit, pray. It's like a student speed writing an entire exam essay without rereading a single sentence. Fast? Absolutely. Reliable? Not exactly. And this exposes a major weakness. The sprinter lacks a real feedback loop. Then researchers found a complete opposite behavior. The sculptor. This personality showed up strongly in Claude Sonnet 4.6. Instead of generating everything instantly, the sculptor behaved more like a human engineer. It followed the classic write, compile, debug, refine cycle. Researchers found that Claude used a medium of 868 terminal commands and averaged over 18 file modification per task. That's massive compared to the sprinter approach. The sculptor constantly interacted with the environment. It would inspect outputs, probe the reference binary, test assumption, correct mistakes, and gradually shape the code base over time, almost like carving a sculpture piece by piece, which honestly feels much closer to real world software engineering. But there was another problem. Researchers realized some AI agents were learning how to fake success. Instead of truly solving the task, they sometimes wrote weak tests that only checked whether the program crashed or exited completely. Basically, the AI was gaming the benchmark. So, researchers introduced something called an assertion quality linter. This tool detected weak or meaningless tests and forced the AI to write stronger assertions, and the impact was huge. It reduced fake dummy passes by 5 times. This reveals something incredibly important about AI coding system. The future is not just about which model writes more code. The real question is which model can iterate, debug, and refine like an actual engineer. Because software development is not one shot activity, it's an evolving process of testing, feedback, correction, and continuous improvement. And right now, the sculptures seem more closer to what reality than the sprinters. So maybe the future of AI engineering won't belong to the fastest model, but to the one that learns how to think iteratively, the one that can explore, fail, debug, and adapt, just like human developers do every single day. The new program bench study revealed something the tech industry desperately needed to hear. We are living in a transition period. AI models today are incredibly good at generating code, fixing bugs, and solving isolated problems. But building real world software system, that's an entirely different challenge. Because software engineering is not just about producing code, it's about structure, reasoning, architecture, scalability, maintainability, and long term planning. And those are still deeply human strengths. One of the most important lessons from Program Bench is this: even if an AI eventually passes every behavioral test, that does not mean it built good software. A model could technically recreate the same behavior while producing a system that is painfully slow, inefficient, resource heavy, or impossible to maintain. In other words, correct output does not automatically mean good engineering, and that distinction matters a lot. Imagine two bridges, both successfully get you across the river, but one is elegant, efficient, stable, and scalable, while the other wastes materials, cracks under pressure, and becomes impossible to repair later. Technically, both work, but only one was designed by a great architect. That's the exact gap AI still struggles with today. And according to the researchers, the real bottleneck may not even be the model itself anymore. It's the surrounding system. The agent frameworks, development environments, memory systems, feedback loops, and scaffolding that allow AI to think like an engineer. Because intelligence alone is not enough. Software engineering requires a workflow, a process of testing, organizing, debugging, refining, and making trade offs over time. Right now, AI still tends to choose the easiest path, collapse system into giant monolithic files, and avoid deep architecture decomposition, and optimize for quick success instead of maintainable design. Which is why the role of the software architect remains incredibly important, because architecture is not just coding, it's decision making under complexity, and humans are still much better at that. But here's the exciting part: ProgramBench does not show that AI failed. It shows where the next frontier begins. We already built machines that can generate code. Now the challenge is building systems that can reason, plan, organize, and iterate and engineer software holistically. The industry is moving from code generators to software architects, and that leap may be one of the hardest problems in AI. If you enjoyed this deep dive into future of AI software engineering, subscribe to the channel and comment below. What do you think AI is still missing to become a true software architect?